Good evening, and thanks for joining tonight's TI Technology webinar, hosted by Texas Instruments, where tonight we're going to take a look at some problem strings. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. Tonight, I'm excited to be joined by our panelist, Pam Harris. Pam teaches at Texas State University and facilitates professional learning for teachers K through 12. She's authored several books and online workshops, including Building Powerful Numeracy and Discovering Advanced Algebra. She's been a T-Cube instructor since her days of teaching high school, and she believes in both the power of mental math and using technology as a tool for learning. Pam, thanks so much for joining us tonight.
Thanks for having me, Mike. Good to be here.
We're expecting a large crowd, so your audio is muted. Feel free at any time to send any questions for Pam using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, the session will provide a link to the event certificate of attendance at the conclusion of the event. We hope you don't have any audio issues tonight, but if you do, try selecting Communicate from the very top of the audio broadcast, from the very top of the WebEx menu, and choose Audio Broadcast. At this point, Pam is going to discuss our agenda.
So we've just had the welcome and introductions, and then we'll experience a few problem strings, an instructional routine. I'll define what kind of instructional routine problem strings are. And then we'll distinguish problem strings from number talks. They have some similarities and some differences. We'll do next steps and hang around for the end of the webinar because we'll have a drawing for a free registration to the International Conference from Texas Instruments in 2020.
Pam, thanks so much. You should have control. Feel free to share your screen.
Okay, welcome everyone. So I'm glad to be here tonight. I'm excited to talk to you about some things that I'm interested in lately. A little disclaimer before we get going too much. Tonight's webinar is probably best experienced if you just sort of kind of go along with me and do less of trying to actually do the technology along with me. Tonight will be less of a button pushing, everybody do it while we're doing it, and more of a vision of what's possible. So I'm going to kind of throw a lot at you in an attempt to give you some sense and ideas of what problem strings are, and less of a tutorial in actually doing the keystrokes that we're doing tonight with technology. So maybe put your handheld device down and sit back and just enjoy. So the first thing I want to do is just introduce a little bit about what I think about math. So I used to, my tagline now is that math is figure-outable. I used to believe as a student and far too long as a teacher, I'm a little embarrassed to say, that math was rote memorizable. I actually bought into the myth that math is a disconnected set of facts to memorize and rules and procedures to mimic. I did that well, I enjoyed doing that, I got a lot of kudos for doing that. But what I didn't realize is that what I was doing was sort of fake math, not what real math is. And after I'd been teaching high school for a little while, I landed in some interesting research and then have since dove into a world of real math. And what does it mean to actually mathematize? What does it mean to use my brain in a little bit of a different way than when I do fake math? So we know from neuroscience these days that when we think, parts of our brain light up. I don't have hard science to back this up, but I'm just going to suggest that when I do fake math, when I repeat things that someone's told me to do, when I pull things from rote memory, there's a part of my brain that lights up. But when I mathematize, when I do real math, there is a different part of my brain that lights up. It feels different. I can tell in the middle of a problem when all of a sudden I've sort of gone into non-thinking, grabbing things from rote memory, or when I'm actually using relationships and connections I own and drawing on relationships to solve a problem. So I hope tonight to give you an example, some experiences of what it could be for that part of your brain to fire. Now, you might have already been mathematizing your whole career. You might have, through the fake math that your teachers did when you were taught, as they sort of said, mimic me, your teacher said, show me your work. I would submit most of our teachers actually meant show me my work, mimic me, and then you'll get credit for mimicking my steps correctly. Maybe you were the kid who actually were always mathematizing. Then if that's true, then I hope tonight to show you some ways of helping your students also mathematize, because I think we need a verb for math. Like when we teach kids to read, kids read. When we teach kids to write, kids write. When we teach kids to do math, they do math. Could we have a verb for that? Can we talk about mathematize? I steal this word from a researcher by the name of Kathy Fosno, who said we need a word that means what our brains do, what they do when mathematicians actually do math. What could it be like for us to have a verb for that when we structure the world around us? And so I'll talk about mathematizing. And in fact, as a teacher, then I want to mentor mathematicians. Now, you might smile at that and go, I mean, that's a nice idea. Of course we want to create more mathematicians. But you might pat me on the head a little bit and say, but Pam, my students, maybe you don't know my clientele. My students aren't becoming mathematicians. Most of my students are barely making it through algebra or whatever you teach. So caution, when you read this, mentor mathematicians, I don't mean mentor mathematicians to be. I actually mean mentor mathematicians in the here and now. What would it be like if we actually had kids mathematizing at their level? So just like when we teach kids to write in fourth grade, often states have big writing tests in fourth grade. You guys are math teachers, you don't care. But if you go around any fourth grade classroom in the state of Texas, you'll hear an awful lot of teachers say, okay, writers, today we're going to write, you fourth grade writers. Well, in that same way, those kids are writing at a fourth grade level. But how are they writing? How are they learning to write? They're engaging in the work of a writer. They write, and then the teacher responds to their writing. What could it be like if we had kids mathematize and then we mentored them as mathematicians at their grade level? As we had sixth grade mathematicians, kids mathematizing at an Algebra 1 level. What does it even mean? And so I hope to give you some examples tonight. I'll do a couple of examples that are more middle school and a few examples that are more high school. Again, to give you an idea of two things. What are problem strings, the instructional routine that we can use to help students construct relationships, really mathematize. And then also this idea of what is mathematizing in real math. And I think problem strings is a brilliant vehicle to actually mentor mathematicians. You may have ever seen this graphic. It's been floating around social media a little bit. I put it out a little while ago. I'm not going to talk too much about this tonight. If you're more interested in it, I'll give you some references at the end of the presentation. But for now, I just want to mention that tonight, I'm not going to focus on developing counting strategies or developing additive thinking or developing multiplicative reasoning, but I'm really focusing tonight on developing proportional reasoning and functional reasoning. So my examples tonight will be what can we do with students as we try to develop proportional reasoning and what can we do with students as we try to develop reasoning about functions. You might notice that in the graphic, we're also developing spatial reasoning and algebraic reasoning at the same time. At least I think we can, and ideally we would be. So the next thing that I want to do is I'm going to switch inputs for just a second, and maybe I'll just check with Mike. Mike, do we have any questions so far?
Pam, I don't see any just yet. All
right, just checking.
Thank you.
Thank you. We're going to switch inputs for a sec. So I'm on my iPad right now. The reason I'm on my iPad, this is TI-Nspire app on my iPad. Let me tell you what I would actually be doing if I was in a classroom. We're on this funny webinar interface. In a classroom, I would use my emulator of choice. I could use a TI-84 to do this. I could use Inspire, either one. And I would project this image onto the board. So if you can picture that what the kids are seeing right now, my students are seeing, is the coordinate axis, and they're seeing this blue function that we're calling F1. You see that the title is sort of sitting over here, F1 of x. I've hidden what F1 of x is on purpose. It's sort of stuck over there on the side. Now, in a classroom, I would project this on the board, and then I would be able to write on the whiteboard. So to do that, I took a picture of the screen. And so now you're going to see where I'm just in a note-taking app, and there's the picture of that screen. Now I can more easily sort of notate. It's as if I'm writing on a whiteboard while I'm projecting on the whiteboard. Okay, and then I might say something to students like, hey guys, we're going to do a quick problem string today. A problem string is a string or series of problems. Remember that it's totally legal for you to keep track of your mental thinking. So if you want to write something down, you can. But in this problem string, I don't think you're going to need to. I think I really just want your focus and your attention. I give that little spiel to students before I do really any work with them, because I find when I go into classrooms today, especially the older the student gets, that they're really in sort of note-taking mode, that often students are kind of in a mode where they have a piece of paper, they have their notebook out and a pencil, and then whatever the teacher puts up on the board, they kind of copy down. And so they're less cognitively involved in what's happening. Their brains aren't really chewing on the relationships. They're just kind of copying stuff down because they've learned in the past that they sort of get the notes down and then they mimic them in order to get to have success in their math class. But that's not success for me. What's successful for me is that they're actually thinking and reasoning. So I'll give them that little spiel and I'll say, for this one, I don't actually think you're going to need paper and pencil. It's okay if you want it, but for right now, I just want your attention on the board up here. So the first question of our problem string is, what if I tell you, so the function right now is blue, so I'm going to write in blue. What if I told you that that I asked you about f of 4? So the first problem that we're going to ask you about today is, what is f of 4? And then I'll let kids think for a little bit, and then I'll call on somebody. I guess I could let you guys put that in the chat window. How do I find f of 4? Oh, and I might have told my students, hey, we've just been messing around with function notation. Function notation is weird. We're just going to practice that a little bit today. So just run with me. We're not going to spend a lot of time here, but just run with the f of 4. And then I will ask students to explain their thinking. And typically a student would say, well, let's see, if I go over to there's 2, 3, 4. And so if the 4 is the input, I go over to 4, I go up to the function, and it sure looks like that point is 2, 4. And then I might ask, does everybody agree with that? And students are like, yeah, that's cool. And so I'll say, well then, what? Oh, sorry, I'm alive. They'll usually say it's 4, 2. And then I'll say, okay, so what goes on the line? And they'll say, well, so if the input's 4, then the output's 2. And we won't spend a lot of time there, but I'll probably write the point up here, 4, 2. And I'll go, cool. All right, that wasn't hard. Let's just keep practicing function notation just a little bit. So I'll just tell you, well, actually, let me introduce something new that maybe you guys haven't heard before, that we have a different notation that's kind of interesting. And that notation is inverse notation. And so I'm going to say that this right here, which you may never have seen before, is kind of interesting. And what it means is that I'm going to take, in fact, let me switch that. What it means is that the inverse function means that the ordered pair switches. So that's one way to think about this new function that we're going to talk about. So if I have the ordered pair 4, 2, then what would that point be on its inverse? And I'll let them think for not very long, because that's not hard, because I just told them what it was. So I could kind of do this after kids had learned a little bit about inverses, or I could do it actually to introduce inverse notation. And so then typically a kid will say, okay, so they switch. So I'm still in. So they switch. So the y value is now the x value, and the x value is now the y value. And I'm like, okay, well, cool. Then where is that point? So somebody will go over to 2, and they'll go up 1, 2, 3, 4, and they'll say, well, it must be that point right there. And I'll go, that one right there, 2, 4. Okay, that point. So 2, 4 is now, we think that's on its inverse. Okay, cool. And then I might say, great, next question that I have for you. So the next question I have for you is, what is, and we're going to go back to f, so I'll change colors. What is, if I just ask you, I know this won't take long, f of 1/2. And then I'll let the kids look for just a second, and they'll think, and we're just practicing function notation a little bit. Somebody will go over to f of 1/2, and they'll sort of go down a little bit, and they'll go, well, I think it looks like it's about -1. I'm like, oh, okay, so that's -1. So that's the point 1/2, -1. Well, the next question I have for you is, let's go back to that inverse. So where would the inverse be? So if I had, what would the point be? And they're like, well, let's see, we've got to switch those guys, right? So if I switch those, that would be what, -1, 1/2. So what would the function notation look like? The inverse of f would be at -1, 1/2. Again, none of this is really hard. We're just sort of doing it kind of quickly. So at this point, then what? Let's see, we're going to graph -1, 1/2. Did I do that right? You guys have to check me when I'm like this weird webinar format. The chances of me making a mistake is great because my brain hurts. So I think that's right, -1, 1/2. And go on to the next question. Cool. All right, and the next question that I have for you, we're going to stay asking about f. And I'm just going to, this time, change things up a little bit. Now I'm going to say, I'm not going to tell you what the input is, but I want to know what the input is for the output of 0. I'll let kids think about that a little bit. Output of 0. Let you guys think for just a sec. I can let you guys put that in the chat window if you're interested. Let's see. Where's the y value? Yeah, sure enough, the y value is 0 at 1. that right? So we've got the point 1, 0 is on the function. And so we could say, all right, 1, and that would be the point 1, 0. Cool, okay. Oh, well, I think you know where I'm going. I'm going to ask now about the inverse function. So if that's true, what's true about, I'm just going to scoot over here, what's true about F inverse? So would that be 0, 1? And we could, oops, 0, oh, Pamela. Bear with me. I'm just a little nervous. So F inverse at what? 0 is 1. Did I do that right? And so cool. Then at 0, I think we're right here then. Is that the point? So 0, 1. Okay, cool. So we've got kind of some things happening. We got this blue function. We got the red function happening, the inverse of the function. Let's see what our next question is. Next question is kind of similar to that one. I'm again going to say to you on the blue function, on that F chi, I'm not going to give you the input, but I'm going to tell you that the output is 1. I'm not going to spend a lot of time on that. I'm looking for an output of 1. So it gets a little interesting. Kids start to do things like drawing like some lines here, and they kind of find that point there, and they're like, okay, that's the point 2, 1. So that would be input of 2, and so that's the point 2, 1. And then of course, a lot of them are already thinking about what the inverse would be, and is that the point 1, 2? And so let's see, where am I? Over 1, up 2. And somebody at this point is usually starting to say, and I'm not looking at the chat, so if you're saying this in the chat, stop saying it, because I would do the same thing with students. Somewhere along these lines, I've got students that are starting to talk about what they think F inverse is, and I will try to keep them a little bit quiet. I'll wink at them, and I'm like, good, just don't tell anybody. Like, don't spoil the surprise for anybody else. So don't spoil the surprise if you're already sort of thinking about what F inverse might be. So then the next question that I might ask is, let's just do one more on the blue F. What if I asked you for F of 1/4? I'll give you another input. You tell me what the output is. F of 1/4, where would that be? Oh, that's like really tiny, like right in here somewhere. No, all the way down. I don't know. Does that look like about -2? So that would be, Pam. Let me clean that up a little bit. So that would be -2. So what's that point? Is that 1/4? -2. So what would F inverse be? And F inverse of -2 is 1/4. Some of you are smiling because we needed to get some second quadrant behavior happening here, right? That little guy right there, is that -2? 1/4, right there. And I don't want to belabor things too much, except now I'm going to change tacks a little bit. Now I'm going to stay in red. And I'm going to say to my students, hey, what if I said to you, like we kind of have a pattern happening with these red. Let me get rid of these blue dots a little bit here. Kind of have a pattern happening. Oh, I got rid of a little bit much there. A pattern happening with these red dots maybe a little bit. That's kind of interesting. So I wonder if we could use that. I wonder if I could say to you, let's think about that function, the F inverse, and where's that point? How could you figure that out? I'm going to let you think about that for just a second, everybody. Where am I looking to be able to find the output on the red function? Well, we don't have the red function. Pam, what are we going to do about that? We'll give everybody a chance to think. Mike, this is where I really wish I could see the chat.
So far, I see 2 from Rebecca, but I think that might have been from your last question.
Okay.
So I think we got to give them another minute to think. But while they're thinking, we had a question from Rachel earlier. She was asking, what grade level do you feel like the material that you're presenting tonight would be used in?
Excellent. So this beginning string I'm doing right here is probably Algebra 2. It could be Algebra 1 if you do inverse functions. That's not typical. So I'm thinking about Algebra 2. Could be pre-cal if you wanted to review some stuff. But I'm also going to do some work later with middle school content, and then I'll come back and do some work with Algebra 1 and Algebra 2 content. Maybe a little bit of trig at the end. So, excellent question. So are we getting any answers, Mike, for F inverse of 3?
So I saw from Rebecca, you need to look at where y equals 3 on the blue function. And then I saw y equals 8, and someone else said 8. And then I agree, 8 is really appreciated.
Cool.
How Rebecca worked her answer.
Oh, interesting. So let's take a look at where the blue function, so I'm going to change my color to blue, where the blue function has a y value of 3. And where does it have a y value of 3? Sure enough, over here at 8. Okay, well, that's interesting. So if the blue function has an input of 8 and an output of 3, then we could expect that its inverse, if it had an input of 3, would have an output of 8. And so where would that be? We'd go over to 3, we'd go up 8, let's see, 3, 4, 5, 6, 7, 8. Oh, up here in my mess. Let me see. Let me move some stuff out of the way. And I think we're right here. Does that look about right? Is that 0.38? Well, that's kind of cool. Okay, so we can sort of use the output to find the input that they can then tell us about the point on the inverse function. And then I might end the string with saying, hey guys, I wonder if you recognize what that inverse function is. What if I wanted to know what that inverse function is at any x value? So I'm going to pause again and wait and see what you guys are putting in the chat now. I don't know if anybody spoiled the surprise earlier by throwing a function in the chat. Mike, are we seeing any answers?
Someone asked if you could please restate your question.
You bet. So we now have this blue function up here, which we don't know what it is, but we have a red function that feels familiar. There's some relationships happening in the red function that feel familiar, and I'm wondering if anybody could tell me what the red function is. So if we decided that it was true for all the numbers in between and we sort of connected some of these guys, I wonder if this function looks a little bit, oh, that's really disastrous. This red function, wow, good, Pam. Undo. Looks a little bit familiar with a function that maybe we've dealt with before. Are we getting anything, Mike?
Yeah, we have. Natalia says that it's a reflection over y equals x. And then Rebecca said that the red function is an exponential curve, and we're even seeing more specific functions like maybe like a 2 to the x. I see a lot of people writing in.
And sure enough, if we were to sort of test out everything, we're getting y equals 2 to the x. Cool, guys. So if I'm still talking to students, that's excellent. We recognize this exponential function that we've dealt with before. That's really cool. And its inverse function is this one that doesn't feel as familiar. Like, I don't know, it kind of looks like some square root things that we've looked at before, but it's in the fourth quadrant. I wonder what this blue function could be. And that could potentially be a lead-in to logarithms. So I actually start with a logarithm and then let students think about what the inverse, whoops, that's not what I want to do, what the inverse of a log function could be. And I'm trying, hang on, what do I want to do? Not that. I know what I'm trying to do. I think I'm on Inspire. I'm trying to move that label over, the F1 of X. I'm trying to scoot it, but I'm on Inspire. I'm on Notability, not in my Inspire, so I can't do that. So, but what I can do, remember, I'm pretending that I'm projecting on my whiteboard. So at this point, this is my whiteboard, and I would have drawn all that on my whiteboard. At this point, I can say to them, well, let's take a look at what this function is. Sure enough. That's kind of cool. Who's ever heard of a logarithm before? Hey, you might have heard of that. All right, cool. This is a logarithm. The inverse of an exponential is this thing that we can call a logarithm. Let's check and make sure, and then I could actually go to sort of some functions, and I could make sure that, that's not what I want to do. That sucker on. Turn on. There's our y equals 2 to the x. Now, ideally, I would have been on the whiteboard, and all those points that we had just plotted in red would now be sort of, and I had connected them, and the graph would cover it, and I could use technology to sort of support, sure enough, this thing that we were looking at that's blue, called logarithm, and this thing that we thought was y equal 2 to the x, it actually is. Cool. All right, great problem string today, guys. Now let's talk more about logarithms. So a way to use a problem string is to introduce a concept. I don't know if you remember, but when I started the problem string, I sort of started it by saying, hey guys, let's practice function notation a little bit. We've been messing with function notation, let's practice that. So ostensibly, I say to kids, let's practice this thing. It's a little weird. Function notation's kind of strange. We just made it up. It's social knowledge. It's by convention that we do that. So let's practice that a little bit. But in reality, I have a different, or at least an additional focus or goal for the problem string, which was to introduce the inverse of an exponential function and walking into logarithms. There's other ways that I could use this particular problem string, but this is an example of a problem string that's intended to help kids build a model and a big idea. So the model of the inverse of a function and the big idea of logarithms. So with that in mind, I'm going to switch inputs real quick. go. And I'll just show you, this is what the problem string looked like on my paper that I was reading as we did this particular problem string. So sometimes it's not very helpful to just see kind of a naked problem string without instructions or some sort of help about, like what the author's intent is for you to do with the problem string. You might not even know what to ask or, what to do or, with the thing. In the write-ups that I have several write-ups on my webpage for free, and then there's also a couple books that I've written that then have helps that would show you like an example screen of what it could look like at the end, like you guys just saw. But you also might, if you ever just see a naked problem string, you might want to ask the author, what was your intent? What would be the kinds of questions that you would ask? So this is an example of a problem string, a string or series of problems intended to create relationships in the learner's heads so that strategies, models, or big ideas become natural outcomes. Before we do a whole lot more, I'd like to do another example of a problem string with you, and then we'll actually define problem strings, and then we'll get some more input from you guys. So to do that, I'm going to change inputs one more time. And now I just need sort of a blank canvas. Okay. Hey, let's do a middle school problem string. So any middle school teachers in the room? If I don't, I think an Algebra 1 teacher could also get some mileage out of a problem string like this. I think any teacher of higher than middle school could get mileage out of things that perhaps middle school students didn't ever learn in middle school. But it is specifically targeted. I wish teachers were doing stuff like this in middle school. So I might start this problem string by reminding students, remember, I want you thinking and reasoning. I don't want you in copy mode, so make sure you're really paying attention. But if you want to jot something down as you're doing your work, it's totally legal to keep track of your mental thinking. In fact, I'll just quote real quick Kathy Fosno again. I mentioned her name earlier. Her name looks like Fosnot, but it's Fosno. Another thing that Kathy Fosno says is that mental math does not mean that you do it all in your head. Mental math means that you do it with your head. Mental math does not mean that you do it all in your head. Mental math means that you do it with your head. So it's totally legal for you to keep track of your mental thinking. If what you're doing is doing some sort of memorized procedure and you do it all in your head, that's not mental math because you're just regurgitating a rote memorized procedure. But if you're actually figuring and reasoning, then you can do it in your head or you can write stuff down. And as long as you're reasoning and using your brain, then you're doing mental math. And I like that definition of mental math. For me, as a numeracy expert, I was not able to become a numeracy expert. I'm saying the word numeracy until I was able to write stuff down, and in a huge way until I was able to see other people put their brains on paper, and then their thinking became take-upable for me. I was able to take up their thinking, and so I highly encourage teachers to model students' thinking, and you're going to see that in this problem string. So, hey guys, we're going to do a quick problem string today. I really like pasta. It's my downfall. And we kind of have this ratio when I deal with pasta. If I think about cups of pasta to the amount of sauce that I need to make to go with, I make a couple different sauces and make a really good marinara. I also make an excellent pesto. Yeah, I know. It doesn't work for my diet very well. But I really like pasta and sauce. And so I have this ratio that if I'm going to make pasta and sauce, with this particular sauce I make, I like to make 8 cups of pasta for 5 cups of sauce. Yeah, can you picture that? Like if I have that amount on hand, then it's going to be a good meal. Oh, you're like, that's a lot of food, Pam. Well, I grew up with 8 siblings, so we always had to have a lot of food in our house. And yeah, it was actually very interesting when I got married and was just cooking for 2 because I didn't really know how to do that. So we always had lots of leftovers. Anyway, moving on. So if this is the ratio that I'm thinking about when I make pasta and sauce, maybe we have some friends coming over, and so I'm going to make even more. And so I need to sort of think about that. What if I've got 10 cups of sauce? How much pasta would I need to go get? I'll let kids think. Not very long on this one at all. And then I might even have a choral response. All right, everybody, how much? I'm not even going to wait for you guys to type anything in, but students are going to say, well, if you double the amount of sauce, then you're just going to double the amount of pasta. Okay, well, that's double 8 is 16. Nobody has to think about that very much. Cool. Well, then, what if I only have 1 cup of sauce? Like it's a bleak day. We don't have it very much, but I'm going to go make some pasta. How much pasta would I make if we've got 1 cup of sauce? Now I'm going to let students work. As I let students work, I'm going to walk around and I'm going to try to keep kids who are getting a quick answer, keep them going a little bit. I might ask them how they explain what they're doing, or I might Just ask them to be patient a little bit, because I will have some students, and I'll look for somebody like this who says, well, let's see, if I've got 5 cups of sauce, let's see if I divide by 5, and then they start thinking about 8 divided by 5. They might even go over here and do 8 divided by 5 and do like work and stuff. And I might have somebody explain, or I might just mention, whoa, some of you guys are trying that. That was some math that you're maybe not all that good at. Some might say, that they can write something like 8 divided by 5. And I might go, okay. Did anybody get a different answer? Somebody's going to have a different answer of 1.6. And I might say, how did you get that? Well, maybe they did the division of 8 divided by 5. But then I'm going to ask the student who I saw, usually this is one who got done a little quicker just because they found this nice relationship, where they just say, well, to get from 10 to 1, I'm just going to divide by 10. And we have this really nice thing in our number system, our base 10 number system, that when I divide by 10, then there's sort of this shifting that happens with the numbers. The numbers sort of shift in the place value table. Now I've got 1.6. And so I can sort of use that to my advantage. Oh, cool. And then students are often like, oh, that would have been nice. Why was I thinking about 8 divided by 5? I could have just thought about the place value switch by dividing by 10. Okay, cool. All right, good. All right, so now we know the amount of pasta and sauce. If we have 1 cup of sauce, we need a cup and a little bit more than a half of pasta. Okay, cool. What if I had 9 cups of sauce? 9 cups of sauce. Again, I'm going to let students work a little bit. 9 cups of sauce. So I'll let you guys work. See what you're coming up with. Mike, maybe you can give me an idea of when a few people have thrown an answer in there. Maybe don't look at other people's answers before you've had a chance to think about how you would figure out the amount of pasta. How many cups of pasta would you need if you had 9 cups of sauce?
So we're starting to get a couple of responses here. So some of them look like they are 14.4. I see some 16 and 1.6 maybe. 8/5, 1 3/5. Against more 14.4s.
Okay. All right, cool. Thanks, Mike. So I would typically find someone that had said to themselves, well, to get to 9, I bet I could take 10 cups minus 1 cup. And then I will, depending on where I am with my class, I might say, oh, okay, so then you're just going to take 16 minus 1 over here. So did you get 15 cups of pasta? I'll let kids chew on that a little bit. If I can find a kid that can handle it, that chose 15, I might actually have that kid explain his thinking. And then I might say, does anybody have any questions for so-and-so who just said that it was 15 cups of pasta? And then the kids, sometimes they'll say interesting things like, does that really work? Like if you had 8 to 5, does that feel the same as 15 to 9? Maybe, maybe not. And then somebody will say, well, wait a minute. If you subtract a cup of sauce, you can't subtract a cup of pasta because we don't know how much we do know that a cup of sauce is 1.6. So you can't just subtract a cup of pasta, not a cup of pasta. You have to subtract a whole 1.6 cups of pasta because we have this relationship here of the 1 cup of sauce to 1.6. Okay, so then what is 16 minus, and that's probably when Mike was reading off the chat, I bet somebody had 16 minus 1.6. So it's not 15 cups of pasta, but it's close to that, but instead it's 14.4 cups of pasta. That's 16 minus 1.6. Okay, all right, that's making some sense. Okay, cool. All right, I'll erase a little bit of that. All right, well, let's see. What if, next problem in our string, let's head over to the other side of the ratio table. What if I've got 4 cups of pasta? How much sauce would I need to make? Let students think about that a little bit. Then I might ask students, hey, did anybody use the 8 cups of pasta? I'm going to pause and let everybody just think about that for a second because not everybody was looking at the 8. Did you use the 8 cups of pasta? Sure enough. So if we divide that by 2, then we would divide this by 2. And what is 5 divided by 2? Is that just 2.5 cups of sauce? Okay. But did anybody not use the 8? Did anybody use the 16? Well, that's nice with 4, right? Can we just divide that by 4? And then we would have to divide 10 by 4. And then we could talk about how kids divided 10 by 4. Maybe they thought about 10 divided by 4 as 5 divided by 2. And then they ended up with the same 5 divided by 2. So we might share a couple of those strategies. And then we could say, okay, cool. So now we know we have 4 cups of pasta. We just need 2.5 cups of sauce. What if I only had 2 cups of pasta? How much sauce would I need? not going to pause too long on that one. A lot of people are just going to go, just cut that in half. Okay, so we'll cut that in half. What is 2.5 in half? Is that just 1.25? I know I'm going kind of fast, so I apologize if I'm going too fast for anybody. I would actually do this much slower with kids. It's hard in the webinar. I don't want to bore people. Then I might say, hey, the next question of our problem string is, what if I only had one cup of lowly cup of pasta? How much sauce would I need? A lot of kids at this point are just going to divide by 2 here, divide by 2 here, and then get stymied a little bit. What is 1.25 divided by 2? And then I might ask kids to explain their thinking. What if I have 1.25 divided by 2? How are you thinking about that? Somebody might say, well, I know that I could do 1 divided by 2, and then I'd have that leftover quarter divided by 2. Okay, well, 1 divided by 2, look, there it is. It's like it's already sitting there as 1/2, or I could write it as 0.5. What's a quarter divided by 2? Is that like 12.5? Okay, we might have to make sense of the decimal a little bit. So what's 50 cents and 12.5 cents? Is that like 62.5 cents? Okay, that's one way to do it. But I might also look to see if anybody else thought about dividing 1.25 by 2 and dividing 1.2 divided by 2. That could be another way. And then we have a nickel left over. What can I think about it? Is there a way to think about that? Now I have 60 cents plus that nickel that's cut in half. Would be another way that I could sort of think about that. I won't even finish that one. Okay, cool. So now we have a couple different strategies for thinking about how we get from 1 cup of pasta to sauce. How about one more question? What if I had, let's go back. Let's just make sure we're good on both sides of the ratio table. What if I had 4 cups of sauce? 4 cups of sauce. 4 cups of sauce. Give everybody a chance to think about that a little bit. And I apologize if you can hear me sucking on something. I'm losing my voice, so I do have a Ricola in my mouth, so sorry if that's loud. So 4 cups of sauce, what might one relationship be that you could use? And here then I'm going to ask kids to share different strategies. Could you scale up from the 1 times 4 and then multiply 1.6 times 4? And then we could sort of share how they did that. They might multiply the 8/5 times 4. They might have different ways of thinking about that. Sometimes I'll ask kids to share that thinking about 1.6 times 4, can I think about 16 times 4? I happen to know that one is 64. So then if that's a 10th relationship here, then it would be a 10th relationship there. And so what is 64 divided by 10? Is that 6.4? So we could think about 6.4 cups of pasta. Did I do that right? I think so. So that would be one way that kids could think about that. They could also, there's also probably somebody that's going to want to be a little bit more additive in their thinking and think about 5 cups minus 1 cup to get 4 cups. And so they could think about 1.8 minus the 1.6. Is that also 6.4? So a couple different ways that kids could think about that. Cool. Then I might say to them, all right, nice proportional reasoning, guys. Great job. We started with this ratio of 8 to 5, and then you guys really solved a bunch of proportions. Like one of them that you solved is I gave you 9 cups of sauce, and you had to, cool, check out how you guys just solved that proportion using proportional reasoning. What you weren't doing was doing what we typically see in middle school, where they cross-multiply and divide, and they do that half wrong. And when they're cross-multiplying and dividing, they're not really thinking and reasoning proportionally. They're just getting an answer using multiplicative reasoning at best. I'd rather have kids actually thinking and reasoning proportionally. So this is an example of a problem string I could use to help build proportional reasoning in kids. They get the sense of when you scale one number in a ratio, you have to scale the other number in a ratio. And if you subtract from one number in a ratio, you have to subtract an equivalent ratio from the other number in the ratio. You can't, if you subtract 1, you can't subtract 1, because 1 cup of sauce is not good for 1 cup of pasta. That's way too much sauce. Come on, you know that. Thanks for letting me joke a little bit. So then I might say to kids, excuse me, hey guys, what if we were to graph these ordered pairs? Can you picture that? Like if we were to say that cups of pasta were the X's and cups of sauce were the Y's, there would be no order, right? This would be like completely haphazard, points everywhere in all 4 quadrants, right? Like no pattern whatsoever. I can just picture you a little bit. Somebody's like, there's no point. They're only in the first quadrant, Pam. Oh, okay. They're only in the first quadrant because positive cups of pasta, positive cups of sauce. Okay, all right, I can buy that. And then someone's going to, then I'll shoot back. But there's no pattern, right? There's no pattern in the first. They're just everywhere. I would use my hands to kind of put points everywhere. And then I'm hoping that somebody says, well, wait a minute. No, I think there is a pattern here. And then I might say to them, well, let's investigate that pattern. So I'm going to switch inputs real quick, and I'm going to go to my TI-84 on my computer. So I have the points here that we've just used and put them in the list function in the 84. By the way, you could do this on Inspire. You could do it in 84. Since I had done Inspire before, I decided to do 84 here. And then I might ask kids, like, where would we look for these points? And I think one of the best things that we could do with kids all the way along, pick any class, is to ask them to choose good viewing windows. So for them to look at this data and then say, what could a window be where we could see this data? I'm not going to take tons of time to walk through that with you because I have some other fish to fry tonight. So I've already set a window that makes sense, but I think that would be a good one for you to do. And then we'll look at it. I'm like, look at that. They're not haphazard in any way. There's actually quite a pattern there, like a real. Then I might say to students, well, it looks pretty darn linear. We've been writing equations for proportional relations. What would that equation look like? And then I'll ask kids to think about what the equation could be. And we might look back at our data and you can't see the table right now, but I'll put this table up. Did we find a unit rate? Which unit rate do you want? Do you want 1 to 1.6? Or do you want this 1 to that 0.6125? Like which of those? Oh, and I have a typo. That should be 0.625. You guys just ignore that. It's going to be close enough for government work right now. Sorry, I was a little in a hurry when I put these points in earlier. I guess I could do it. Don't hate me. Is that 0.625? Did I do that right? Yeah. Okay. And then, so I've set up a window, and then we'll go look at the graph, and then I'm going to ask kids to write a function that could represent that. And so which of those might I want to use? I'm going to let kids think about that. I might even let them put it in their calculator, depending on how much button pushing I want to do that day, and we'll get that unit rate in there, and then we'll take a look at that function. So I think I can use technology to help me do this quickly to sort of get the sense of, oh, yeah, sure enough, we wrote the right function that could represent the relationship that we just looked at, more than the relationship we looked at, because this one's going to be in the third quadrant as well. And it's also going to be in between, lots of different measurements, lots of pasta and sauce, and all the measurements in between. So this is an example of a problem string that I might use to help students build proportional reasoning. Let's take a look at the definition of a problem string. So problem string is a purposeful sequence of related problems designed to help students mentally construct mathematical relationships. It's a powerful lesson structure during which teachers and students interact to construct important mathematical strategies, models, and concepts. The power of a problem string lies in the carefully crafted conversation. So that kills me right now because you just kind of had to hear me sort of invent the conversation based on experiences I've had with students. I wish we could have had one live. As students solve problems one at a time, and the teacher models student thinking and draws out important connections and relationships. So a couple of important things to realize about problem strings is, and by the way, I'm going to give you a free download at the end of today's presentation where it will have this definition and more about problem strings. So a couple things to realize is that problem strings are meant to be highly interactive. They're never intended for students to just look at a problem string to do on their own. You'll notice that if I just would have given you that one and said, go do it, you wouldn't even know what to do, right? But also, beyond the fact that you would know what to do, then you don't have the rich conversation that could happen as you share strategies, especially in the string that we just did where we had different strategies happening. Then that rich conversation doesn't happen if you do it all by yourself or all alone. So problem strings are intended to be highly interactive where there's a carefully crafted conversation as students solve problems one at a time, and the teacher represents student thinking to make it visible, and then drawing out important connections and relationships. I'm going to take a breath and ask Mike if we have any questions that we need to answer in the chat.
Pam, I'm not seeing it. I know we have a lot of great interaction so far tonight, but so
okay,
that's
cool.
a good thing.
Yeah, excellent. Okay, so I'm looking at the time, and I'm trying to decide. I have two things I have planned, and I've got to choose which one. They both kind of hit the same grade level, so that won't be helpful to ask you who got more on. let's take a minute and think about how a problem string could actually be used in a sequence of teaching. I like to use problem strings that are related to what I'm doing in that day to support the learning. So I'm going to whip through this pretty fast. Hold on tight, and then if you want to kind of come back later to examine how it goes more, than you can. So the very first thing I'm going to do is do a quick problem string with you. So I'm going to switch my inputs back to where I am writing on my iPad. Okay, so I might say, hey guys, we're going to do a quick problem string. Do this with me really fast. I don't think you're going to need paper and pencil. I'll give them a spiel again about mental math. And then I'll say, okay, cool. What if I asked you 4 times what is 20? I know that feels like a third grade question. Hang in there, Algebra 1, Algebra 2 students. Just what is that? I know you guys all know that's 5. Okay, and did anybody think about getting that 5? A lot of you guys just said 4 times what is 20 and it was 5. But anybody think about that as 20 divided by 4? Like, could you take the product divided by the factor you know to get the other factor? You could? Okay, all right, cool. Here's the next question. What if I said 4 times something is 21? Now I'm going to let kids work. Let them work, let them work. And then I'm going to say, hey, did anybody use the problem before to help you? And a lot of kids are going to grin and smile and say yes. And I'll have them talk, and they usually say something like, well, I know that 20 divided by 4, or 4 times 5 is 20. And when they say that, I'll go, oh, okay, so you know that. And then they'll say, yeah, but we have 1 left over. And I'll say, okay, you have 1 left over, and you have to divide that by 4 as well. Okay, what is 5 and a fourth? And then they smile, and we'll say it's 5 and a fourth. Okay, cool. Here's the next question. What if I said 4 times something is 23? Let kids think about that. And I know I'm going kind of fast, but I'll say, did anybody kind of use the same sort of thinking? Did anybody think about the fact that you already knew that 20 divided by 4 was 5, and now you have 3 left over? Okay, what's 3 divided by 4? Is that just like 3/4 or 5.75? I also might ask, did anybody think about 24 divided by 4 in order to think about 23 divided by 4? In fact, let me write that this way. Can I think about 23 divided by 4 as 24 divided by 4, but minus that extra 1 divided by 4? Is that just 6 minus a quarter? Okay, that's also 5.75. Cool. Nice job, guys. All right, here's the next problem, our string. We've been doing a lot of sequences lately. Sequences. You guys are doing great. Just do a couple more with me. What if I say to you that I've got a sequence, and the first term is 5, and that's a comma, and the second term is 20, and then there's more terms. And I told you I got there by multiplication. What would that missing factor be? Yeah, I know that's not hard, everybody. That's just 4, right? Could I also do this kind of the same thing that we were just doing? Could I say that the second term of the sequence divided by the term before it, if we know that what was happening was multiplication, could I write that way? Okay, right? Would that also give me that 4? Okay, cool. Here's a new sequence. The first term is 5 again, but this time the second term is 22.5. More terms, and I tell you I got there by multiplication. Go ahead and think about that. Thinking. How could I find that missing factor? Again, because of time, I'm going to ram a little bit quickly here. Could I think about 22.5 divided by 5 as that 20 divided by 5 plus that extra 2.5 divided by 5? Well, 20 divided by 5, that's just 4. We already agreed. And then what is 2.5 divided by 5? Is that just a half? So would this be 4.5? Okay, that's interesting. So it looks like when we know a product and one factor, we can use division to find the other factor. All right, I don't know if that's helpful, but we'll see. Okay, second to last problem of our screen. We've also been doing a lot of sequences where we've put them in tables. And we've sort of had a table where we had the term number, and then we had the term. Well, I'm telling you that term number 1 of this sequence is 12. And term number 2 of this sequence is 6. And I'm telling you that we got there by multiplication. Wait. Oh, shoot. Do I have a typo? Is 12 to 6 with multiplication? Multiplication can't end up with a smaller number, can it? Okay, I'm winking a little bit here. I'm going to push up against kids. I want them to think about this idea. Can I get from 12 to a number smaller than it by multiplication? And somebody's going to say, well, I know it's half, and I'm going to maybe say to them, could we do kind of what we did before? Before you told me that we could take the second term, And we could divide it by the first term to get that missing multiplier. Oh, that's equal to 1/2. Well, that seemed kind of helpful. Okay, cool. All right, last problem of our string. Again, I'm going to tell you that the sequence, there's term number, and there's term. If term number 1 is 12 again, but this time term number 2 is 9, and I tell you I got there by multiplication. Let kids think about that. Thinking. And somebody's going to say, no, it's not the only way. Often kids will have some really interesting strategies to share how they find this multiplier, but someone's going to say, I took the second term and I divided it by the first term. And I'm going to pull that out of kids. I'm going to make sure that we sort of talk about, we can have the equivalent if we need to on that, but I really want kids to sort of have this feel that if you have a product, a product and a factor, you can take the product divided by the factors to find the missing factor. All right, excellent, guys. Great problem string. That was quick. I know it seemed kind of like stuff that we aren't really working on, but way to find those missing multipliers. Nicely done. Hey, you guys were really excited when you walked in today because, I'm trying to switch my inputs while I talk and it's not. Oh, I know why. There we go. You guys were really excited when you walked in today because you saw that we had, oh, whoops, I'll just tell you, there's the string that we just did. So that's what it sort of looks like naked. I'll go, you guys are so excited because on each of your group tables, you guys each had a different bouncy ball. I know, you've been trying to do stuff with it since you walked in the room. Thanks for not messing with them yet. With that bouncy ball, today, here's your task. Each in your group, you're going to take your particular bouncy ball for your group, and you're going to put it under a CBR. This is a calculator-based ranger. It's a motion detector, and you're going to hook it up to your graphing calculator, and then you're going to drop that ball underneath the motion detector. Right now, he's dropping it above it, but we could drop it above or below. And then you're going to collect some data, and that data will look, so like there's an example below. You're going to collect data, and what I really want you to do is focus on, of that data that you collect, I only want you to grab the max heights of each bounce. So you're going to collect data, max heights of those bounce, and when you do, it should look something like this. Go. And then I'm going to walk around to each of the groups, and of that data that they all collect for their individual bouncy balls, I'm going to instruct them as I walk around to create. Now, it kind of depends on what we've been working on. If we've been working on geometric sequences, I'm going to ask them to create a geometric sequence. If they've been working on exponential functions, I'm going to ask them to write an exponential function. After they write their either one, geometric sequence or an exponential function, then I might say to them, hey, cool, let's come together. And then if you want to, ask me later why I call this a math congress, but basically we pull all the kids together and then I say to them, hey guys, check it out. Here are all the geometric sequences that you wrote for your bouncy balls. What I'd like you to do now is with your partner, I'd like you to put them in order. Which ball is which and in order of bounciness. Now, unfortunately, I'm running short on time, so we're not going to take a lot of time here, but I would have the kids parse out how they know which one's bouncier, and by doing that, they're really working on the parameters of a geometric sequence. Or I could give them the exponential functions, if that's what we're working on, and they could be working on the parameters of an exponential function. So I could start the day with that problem string that helps them then deal with this data in such a way, because all of the multipliers that they're going to find, and you'll notice if you look at these exponential functions, all of the multipliers are less than 1 because the data is decreasing. So I sort of got those ideas percolating by the problem string that they can then use as they write their functions, and then they can use those, get better at those parameters as they sort of sort the ones that they all came up with. Well, then we might get together the next day and I might say, okay guys, cool, let's do a quick problem string. So, hey, remind me, was this the basketball from yesterday? Let's see, that means we dropped it from a height of 0, and then it had 75% return height. Okay, what does that look like on the graph? What does that look like in the ball? Okay, cool. What if we change it like this? And then I have the kids tell me how that would change in the ball and how that would change in the graph. And then we could graph it. I'm not going to take the time to do it right now, but we could graph that change. I could do this with exponential sequences or geometric sequences. I could do it with exponential functions. Then I might ask them from the first one, how did this change? From the first one, how does this one change? And again, we're making connections between all the representations. And the last problem of the string might be, here's some more raw data. New raw data, take that raw data, what can you do to write an exponential function or a geometric sequence, depending on which one. So what you've just seen is a sequence of how I could use the problem string to sort of help kids learn the content that I'm trying to get them to learn through a rich task, where I could use a problem string before the rich task to get ideas percolating that I need to have happen in the rich task, and then after the rich task, because I'm going to admit that I didn't cinch the learning in the rich task, and so maybe I can use the problem string help cinch that learning. I know I did that really fast. Thanks for holding on tight. Oh, that's what it would look like if I gave them the exponential functions. We're not going to have time to do that one. Sorry. I'm not going to have time for questions either. I'll just end with saying I believe that teaching math is about relationships among numbers and structures to solve problems, and between teachers and students to nurture and mentor young mathematicians. If you'd like to connect with me, this is my website, mathisfigureoutable.com. If you go to my homepage, it says that you can submit your first name and email to receive weekly emails to help you become the math teacher you want to be. I think they're actually kind of helpful and somewhat funny. So if you're interested in connecting with me, that would be an ideal way to do it. Here's the numeracy books I wrote. Here are some algebra problem strings books I wrote. The problem strings we did tonight are all from these two books. Best place to buy them is Kendall Hunt if you're interested. Just as a disclaimer, I don't get any royalties from these. I wrote them for a fee. And tomorrow night, Wednesday nights at about 8 o'clock Central Time, we do a thing called Math Strat Chat. It's one of my favorite things these days. I literally throw out a question, and then I ask people from around the world to submit their solutions. And it's been a blast to just have people put solutions in that are unique and fun and really mathematizing. So check me out on Twitter, Facebook, or Instagram, where you can see a problem of the week, and you can sort of lurk and see what other people do, or you could submit your own strategy. It's a lot of fun. We'd love to see you there. Coming up, just so you know, I'm running an online workshop on building proportional reasoning, like that proportional reasoning string we did tonight. I'm also starting a leadership academy, so if you want to know when those are happening, you could subscribe to mathisfigureoutable.com. If you'd like to download, I said earlier, the definition of problem strings, you can go to mathisfigureoutable.com/intro. That's an introduction to algebra problem strings. It'll tell you lots about problem strings. The top link, that bit.ly link, is a paper that's all about ratio tables. So if you're a middle school teacher and you were interested in what I did with that ratio table with the pasta and sauce, that's a link that you could click on to or go to download a paper all about ratio tables. All right, Mike, thanks. I'm done. Woo.
Thanks so much, Pam. I think that was all one breath. So nice job. Now you can take your second breath. As we wrap things up, a couple things that we wanted to mention for tonight. First thing, sorry, let me take things back, Pam.
Yeah, I was trying to help you. I never can do that.
I got it. First thing, as Pam mentioned earlier, we are excited that the T-Cubed International Conference is coming to Dallas in mid-March of 2020. It's going to be here before you know it. I know that if you visit our website, education.ti.com, you can learn more about the conference as well as, I think, get some special pricing currently while it's still available. It's a great place to connect with other educators that are like-minded and learn some new things. So we hope to see you at the T-Cubed International Conference. And for one lucky winner tonight, a free registration. And tonight's lucky winner is Gloria Chen. So, Gloria, congratulations at the T-Cubed International Conference. And Gloria will be sending an email to you in a couple of days to give you a little more information. To receive a certificate of attendance for tonight, go ahead and click the link in the chat window. Let me try and send that one more time. There we go. Clicking those links will get you a link to the certificate and a link for the documents from tonight. And if you are watch this on demand, go ahead and copy that link into your favorite browser to receive your certificate. Also, I want to mention that we have a promotion contest right now on our website called the Extra Credit Contest. Doing things that you already normally do as a teacher will gain you entries into the contest, which means potential drawing winnings. So doing things like attending a webinar like tonight, you can earn entries into the drawing. Its code is not case sensitive, and it's all one word, and it's prob strings. So I'm putting that in the chat window as well. So again, feel free to visit our website, education.ti.com, to learn a little more about the extra credit contest. Thanks so much, Pam, for everything you shared tonight. We really enjoyed it, and we hope to see everyone back online real soon.